Now you might have noticed so far in the course that we haven't made any changes to the actual physical circuitry of our CPU. All we've done is we've built up a piece of software which will help us generate the assembly language code. That is, we've built up an assembler and a debugger. Now there's nothing wrong with that because we want to be able to write out the assembly language in a much more easier and efficient manner. But it's not the only route we want to take. So let's say, for example, we decide to sell our CPU as it is to, say, a company which predicts the weather. Then they would take our CPU, they would try it out, and then they would get back to us. And they would say something like, well, we tried to run our algorithm on your CPU, and we found out that the algorithm that we normally run over a 24-hour period, which will predict the weather for the next week, we predict it would take 10,000 years to run that same algorithm on your CPU. So you're left with the problem of trying to make the CPU faster. Now we could make the CPU faster by simply increasing the clock rate. Now we could increase it to, say, 3, 4 or 5 gigahertz. But that would only decrease the time it takes to run the algorithm from, say, 10,000 years down to 2,000 years. So we're still a long way off. So in order to make this CPU run a lot better, we're going to have to come from it from a couple of different angles. We're going to have to change the actual physical circuitry of the CPU in order to make it run a lot more efficiently and a lot quicker. But we're also going to still continue to make the assembler and the debugger better to make it easier for us to actually write the code. Now we're going to have to physically change the CPU as well. Say, for example, we might require more registers because it's very difficult to write our code with maybe just the 4 registers we have at the moment. So there's lots of changes that we're going to see over the next 5 or 6 videos. The changes we're going to create are going to be changes in the actual physical design of the CPU. So let's quickly go over the roadmap for the next 5 or 6 videos. So first of all, we don't want to use the version of Logisim that we have at the moment. There are other versions of Logisim which are supported, and they're much more robust. And I've actually chosen one called Logisim Evolution, and I will have a video that will show us how to port all of our designs onto the Logisim Evolution. Now it's a bit of a pain, but it's well worth doing because it just runs a lot faster and it's a lot less buggy, and it makes everything over the rest of the course a lot simpler. So it's well worthwhile going ahead and porting it over to Logisim Evolution. And as it sounds, it's very similar to the original Logisim. There's just a little bit more functionality involved in it. Now, whenever we've ported it over, I want to make sure everyone is able to run their CPU. So if you can't get it running, then give me a shout so we can work together to make sure that your CPU is ready to start in the Logisim Evolution environment. Now, the other things that we're going to look at over the next 5 or 6 videos are getting rid of this RAM element. So this is a bit of a bottleneck and it slows our running of our CPU down considerably. So what we want to do is we want to take this RAM element that we've generated and we'll take it outside of the CPU. So it would sit here. Now, in effect, you could think about this RAM element as your, say, you would have your CPU, and then you would have a rack of 4 8 megabyte RAM sticks. Okay, so once we've taken the RAM element out, we want to replace it with a simple Logisim RAM, because that's going to run super fast. And we're not going to lose any of our understanding because we know how the RAM works. If you've designed it from the first course, we know what how the RAM works. And we can think about the RAM as simply an input and an output. And we can replace our slow RAM with the Logisim fast RAM. Now, another thing that we're going to look at is how we get information into the CPU and out of the CPU. Now, we've actually already got that built into the control section, but I never covered it in the first course. So we're going to have a much simpler way of loading up the CPU. So that simpler way, it will get rid of this whole thing here. Okay, and it will also get rid of a lot of the details that we have within the control section. So we won't have this other counter here, so we could get rid of this section here. And also within the control section, you can see it's a bit of a mess at the moment. We've got all this little bit of circuitry here in order to get it running properly, and there's another section here. So there's lots of stuff that we can get rid of by using the correct method of bringing data into the CPU and taking data out of the CPU. Now, another thing that we can look at whenever we do that is generating a memory mapped I/O. So we could have not just external RAM, but we could have other elements there, which at the moment they would be quite simple, but they would later on they would represent a keyboard, a monitor, a mouse, for example, and we'll be able to get information from the CPU to each of those devices using a memory mapped I/O. Now, another thing we'll look at is the reset, because the reset at the moment is a bit contrived because it's dependent on the output and input pins here. And if we look at the attributes, so it's dependent on us setting these attributes, and I've set them all to pull down. So that's part of the reset mechanism that we have at the moment, and we want to get rid of that and just build a little reset, a proper reset into the CPU. And again, that's nothing too big. We'll work through that together and we'll get that done. Now, the main thing though, what we want to look at is the actual control unit. So the control unit that we have at the moment is a hardwired control unit, and it was a nice way to get a lead in to how we're actually generating the instruction set. But what we can do is we can replace this hardwired control unit with something called a micro-coded control unit. But even whenever we do that, there's still going to be some decisions we're going to have to make, because we could make it completely micro-coded, but then the microcode would be very large. Okay, so it would be a very large lump of code. Now what we can do is we can get a balance between the hard wiring and the microcode, and you'll see that balance being generated as we work through that process. But we'll end up with something called a micro-coded control unit. And also we're going to expand everything to 16 bits. So when we expand to 16 bits, that's really going to give us a lot more power than we have at the moment. And we'll also look at adding some other ideas, like adding a stack and a stack pointer. But we'll get to that over the next half a dozen or 10 or so videos. So that's the general route. So the first part that we've done so far in the course has looked at the generating software, that's the assembler debugger, that will allow us to run, generate and run and test our code before we actually load it. This part of the course is going to look at updating to the new Logisim Evolution and changing the actual physical structure of the CPU to make it run a lot faster and make it so that it's a 16-bit machine. So that's the direction we're going over the next 10 or so videos. So stick with it, and I'll get you on the next video. Goodbye.